What if I told you that the greatest journey humanity could ever conceive would require not years, not centuries, but millions of years to complete? A voyage so vast that entire civilizations would rise and fall before reaching the destination? The Andromeda Galaxy, that faint smudge of light visible on dark autumn nights, beckons from an almost incomprehensible distance. It's our nearest major galactic neighbor, and yet the gulf between us represents one of the most formidable challenges physics can present. To fly from Earth to Andromeda isn't just difficult. It's a journey that would test every limit of human ingenuity, patience, and our very understanding of what's possible in this universe. The Andromeda Galaxy sits 2.5 million light-years from Earth. A light-year, the distance light travels in 1 year, equals nearly 6 trillion miles. Even traveling at light speed, this journey would take 2.5 million years. Before our spacecraft can even dream of crossing intergalactic space, it must first break free from Earth's gravitational embrace. A challenge that, while modest compared to the full journey, requires enormous energy and serves as our first major hurdle. Our planet, despite being a small rocky world in cosmic terms, holds everything on its surface with tremendous gravitational force. This invisible tether must be severed before we can venture into the depths of space, and doing so demands we reach what physicists call escape velocity. Escape velocity is the minimum speed needed to break free from a celestial body's gravitational pull without any additional propulsion. For Earth, this critical threshold sits at approximately 25,000 miles per hour, or about 11.2 kilometers per second. This means our Andromeda-bound spacecraft must accelerate to this breakneck speed just to leave our planet behind. To put this in perspective, a commercial airliner cruises at roughly 575 miles per hour. Our spacecraft needs to go more than 43 times faster just to escape Earth. The energy required is staggering. Every kilogram of spacecraft mass demands immense amounts of fuel to accelerate, and that fuel itself has mass that must also be accelerated, creating a tyrannical equation that has plagued rocket engineers since the dawn of spaceflight. Current rockets achieve Earth escape velocity through chemical propulsion, burning vast quantities of fuel to generate thrust. The Saturn V rocket that sent astronauts to the Moon weighed 6.2 million pounds at launch, yet could only send a tiny 100,000-pound payload toward our natural satellite. Most of that colossal mass was fuel, burned in minutes to achieve the necessary speeds. For our Andromeda mission, chemical rockets are woefully inadequate. They simply cannot carry enough fuel to reach the velocities we'll need, which must be thousands of times greater than escape velocity. But escaping Earth is only the first step. Our spacecraft must also overcome the Sun's gravitational influence, which extends its grip throughout the entire solar system. The Sun, containing 99.8% of all mass in our solar system, creates a gravitational well far deeper than Earth's. To truly leave the solar system behind and enter interstellar space, our craft must reach solar escape velocity from Earth's orbital position, which is approximately 94,000 miles per hour, or 42 kilometers per second. This is nearly 4 times Earth's escape velocity, demanding exponentially more energy. The Voyager probes, humanity's most distant ambassadors, achieved this feat through a combination of powerful rockets and gravitational assists from the outer planets. Jupiter and Saturn acted as cosmic slingshots, stealing a tiny bit of their orbital momentum to fling the spacecraft faster and farther than rockets alone could achieve. For our Andromeda mission, even solar escape velocity is laughably insufficient. We need speeds approaching a significant fraction of light speed, perhaps 10, 20, or even 50% the speed of light, to make the journey conceivable within any reasonable time frame, even by cosmic standards. At 10% light speed, the journey would still take 25 million years. At 50% light speed, we're looking at 5 million years. These velocities are so far beyond our current capabilities that they represent not merely an engineering challenge, but a fundamental reimagining of propulsion technology. We're talking about speeds of 67 million miles per hour for 10% light speed, or 335 million miles per hour for half light speed. Velocities that make our current fastest spacecraft look as though they're standing still. The energy requirements scale catastrophically with speed. Kinetic energy increases with the square of velocity, meaning doubling your speed requires 4 times the energy, tripling it requires 9 times the energy, and so on. When we're talking about accelerating even a modest-sized spacecraft to relativistic speeds, those approaching light speed, we're discussing energy levels that dwarf anything in human experience. We would need energy equivalent to millions of nuclear weapons, or the total electrical output of human civilization for centuries, just to accelerate a single spacecraft. And remember, we must accelerate all that mass, including whatever propulsion system and fuel we're carrying, making the problem even more complex. This is why leaving Earth and the Sun's gravitational influence, while being the first challenge, sets the stage for everything that follows. We must achieve speeds that current physics and engineering can barely theorize, let alone build. The rockets that took us to the Moon, that sent probes to the outer planets, that represent our greatest triumphs in space exploration, are primitive campfires compared to the fusion furnaces we would need to even begin this journey. Escaping Earth's gravity well isn't the hard part of reaching Andromeda. It's merely the moment we realize just how unprepared we are for what lies ahead. As we contemplate the tremendous velocities needed for our Andromeda journey, we collide headfirst into one of the universe's most fundamental and immovable laws, the cosmic speed limit. This isn't a suggestion or an engineering challenge to be overcome with better technology. It's a hard boundary written into the very fabric of reality itself. Understanding why we can never reach light speed requires us to explore Albert Einstein's special theory of relativity, published in 1905, which revolutionized our understanding of space, time, and motion. Einstein's special relativity revealed that space and time are not separate, absolute entities, but are interwoven into a single continuum called space-time. One of the theory's most profound implications is that the speed of light in a vacuum, approximately 186,282 miles per second, is not just the fastest speed observed, but the fastest speed possible for anything in the universe. Light speed is the same for all observers, regardless of their own motion, a fact that seems counterintuitive but has been verified through countless experiments. If you're standing still and measure a beam of light passing by, you'll clock it at light speed. If you're traveling at 99% light speed and measure a light beam overtaking you, you'll still measure it traveling at light speed relative to you, not at a mere 1% faster than you're going. This strange constancy leads to even stranger consequences. As objects with mass accelerate closer to light speed, relativistic effects begin to dominate, and the universe starts behaving in ways that defy our everyday intuition. One of the most significant effects is relativistic mass increase. As an object's velocity increases, its mass effectively increases from the perspective of a stationary observer. This isn't because the object is gaining atoms or matter, it's because mass and energy are equivalent, as Einstein showed in his famous equation E equals mc squared. The kinetic energy you're pumping into the object to accelerate it manifests as increased mass. At everyday speeds, this effect is utterly negligible and unmeasurable. But as you approach light speed, it becomes dominant and catastrophic for any propulsion system. At 90% the speed of light, an object's mass has roughly doubled. At 99% light speed, it increases by a factor of about 7. At 99.9%, the factor is over 22. At 99.99%, it's more than 70 times the original mass. This progression continues asymptotically. As you get closer and closer to light speed, the mass approaches infinity. This creates an insurmountable problem. To accelerate this ever-increasing mass requires ever-increasing amounts of energy. To push an object the final distance to actual light speed would require infinite energy, which is impossible. The universe has set a speed limit, not through some arbitrary law, but through the fundamental relationship between mass, energy, and space-time. No matter how powerful your engine, no matter how advanced your technology, you cannot accelerate any object with mass to light speed. You can get arbitrarily close, 99.9999%, or even closer, but never quite reach it. Only massless particles like photons can travel at light speed, and they can never travel at any other speed. This reality demolishes any hope of using conventional propulsion for our Andromeda journey. Chemical rockets, which work by expelling hot gas to generate thrust, are hideously inefficient. The best chemical rockets achieve exhaust velocities of perhaps 4 to 5 kilometers per second. To reach even a tiny fraction of light speed would require carrying impossibly vast amounts of fuel, far more than the mass of the spacecraft itself, indeed far more than we could practically launch or construct. The rocket equation, formulated by Konstantin Tsiolkovsky, shows that the mass ratio between a fully fueled rocket and its empty mass grows exponentially with the desired velocity change. For the speeds we need, this equation yields absurd results. Fuel masses millions or billions of times greater than the payload. Even advanced propulsion concepts struggle against relativity's iron laws. Nuclear propulsion, ion drives, and other technologies can achieve better exhaust velocities than chemical rockets, but they still operate on the principle of carrying fuel and expelling it for thrust. The tyranny of the rocket equation still applies, merely with slightly better numbers. To reach 10% light speed with any reaction-based propulsion system would require either carrying stellar masses of fuel or achieving exhaust velocities that themselves approach light speed, which brings us back to the same relativistic problems we're trying to solve. This is why Einstein's special relativity represents not just a challenge, but seemingly an absolute barrier to intergalactic travel. We're not fighting engineering limitations or technological immaturity. We're fighting the fundamental structure of the universe itself. The speed of light barrier ensures that our Andromeda journey, even under the most optimistic scenarios with propulsion systems that may be theoretically possible, would take millions of years. There is no secret trick, no clever workaround that lets us sidestep relativity. Any realistic approach to such a journey must accept this cosmic speed limit and work within its constraints, pushing as close to light speed as possible physics allows, while acknowledging we can never quite reach it. Given that conventional propulsion systems are completely inadequate and that the speed of light remains an unbreakable barrier, we must turn to more exotic and theoretical propulsion technologies that might at least make our Andromeda journey conceivable, if not practical. These systems exist primarily in theoretical physics and engineering papers, but they represent humanity's best ideas for how interstellar and eventually intergalactic travel might someday be achieved. Each offers unique advantages and faces daunting challenges, yet even the most optimistic projections reveal that our journey would still consume millions of years. Antimatter propulsion stands as perhaps the most powerful, theoretically possible rocket system. When matter and antimatter meet, they annihilate each other completely, converting 100% of their combined mass directly into energy, according to Einstein's E equals mc squared. This is the most efficient energy release possible in the universe. Nuclear fusion, by comparison, converts less than 1% of mass into energy. An antimatter engine would work by bringing small amounts of antimatter into contact with normal matter in a controlled reaction chamber, producing tremendous amounts of energy that could be directed as thrust. The exhaust velocity of such a system could theoretically approach a significant fraction of light speed, making it far more efficient than any chemical or nuclear rocket. A spacecraft using antimatter propulsion might achieve 10 to 30% of light speed, potentially reducing our Andromeda journey to only 8 to 25 million years. However, antimatter propulsion faces staggering practical obstacles. Antimatter doesn't exist naturally in any significant quantity in our region of space. We must manufacture it particle by particle in massive accelerators like CERN at tremendous energy cost. Currently, we can produce only tiny amounts measured in individual atoms. Creating and storing the kilograms or tons of antimatter needed for interstellar propulsion would require energy outputs exceeding human civilization's total current capacity by enormous factors. Additionally, antimatter must be stored without touching any normal matter, requiring magnetic containment systems that themselves demand constant power. A single containment failure would result in a catastrophic explosion. Nuclear fusion propulsion offers a more achievable, though less powerful, alternative. Fusion is the process that powers the Sun, forcing light atomic nuclei together under extreme temperature and pressure to form heavier elements, releasing energy in the process. A fusion rocket would use this energy to heat and expel propellant at very high velocities. Various designs have been proposed, from the Project Daedalus concept of the 1970s to more modern ideas involving magnetic confinement fusion. Fusion rockets could potentially achieve exhaust velocities of 3 to 5% of light speed, allowing a spacecraft to eventually reach cruise velocities of perhaps 5 to 10% light speed after extended acceleration periods. This would still mean a journey time of 25 to 50 million years to Andromeda. The challenges here are significant, but not necessarily impossible. We haven't yet achieved sustained, controlled fusion reactions that produce more energy than they consume, despite decades of research. The temperatures required, tens of millions of degrees, and the magnetic fields needed to contain the fusion plasma are at the extreme edge of materials science and engineering. A spacecraft-scale fusion reactor would need to operate continuously for decades or centuries during the acceleration phase, with perfect reliability, while producing enough thrust to move a massive vessel. Solar sails represent an entirely different approach, one that requires no onboard fuel at all. These vast, ultra-thin reflective sheets would be pushed by radiation pressure from sunlight, or, more practically for interstellar journeys, powerful lasers beamed from the solar system. When photons strike a reflective surface, they transfer momentum, creating a small but continuous thrust. The advantage is elegant. No fuel to carry means no tyranny of the rocket equation. A solar sail could theoretically accelerate continuously as long as the light source remains strong enough. Projects like Breakthrough Starshot have proposed using ground-based laser arrays to push gram-scale probes with light sails to 20% of light speed, potentially reaching nearby star systems in decades. For Andromeda, even at 20% light speed, we're looking at 12.5 million years, and that's only if we could build laser systems powerful enough to push the craft across interstellar distances. The beam would need to maintain coherence and power across light years, a seemingly impossible engineering feat. For a crewed mission requiring a much more massive spacecraft, the sail would need to be monumentally huge, perhaps hundreds or thousands of kilometers across, and the laser array would need to be correspondingly more powerful. Deceleration at the destination presents another problem. There's no laser array at Andromeda to slow you down, so you'd need a second sail facing backward or some other braking method. Each of these propulsion systems represents a radical improvement over anything we currently possess, yet none can overcome the fundamental constraints imposed by physics. Even antimatter propulsion, the most powerful conceivable rocket technology, might push us to perhaps 30 or 40% of light speed at best. and that's with optimistic assumptions about efficiency and engineering. This would reduce our journey to Andromeda to roughly 6 to 8 million years, still an incomprehensible span of time. The harsh reality is that reaction-based propulsion, no matter how exotic, faces diminishing returns as speeds increase due to relativistic mass effects and the exponential fuel requirements. We might dream of technologies beyond even these: warp drives that bend space-time, wormholes that puncture through space. But such concepts remain purely speculative, with no clear path to realization and questionable compatibility with known physics. For any journey we might actually contemplate with technologies that could potentially be developed, Andromeda remains millions of years distant, emphasizing that this voyage would be unlike anything humanity has ever attempted or even seriously contemplated. While the absolute distance to Andromeda remains fixed and the speed of light sets an immovable cosmic limit, Einstein's theory of relativity offers one genuinely astonishing silver lining for any crew attempting this journey: time dilation. This phenomenon, one of the strangest and most counterintuitive predictions of special relativity, means that time itself passes differently for objects moving at relativistic speeds compared to stationary observers. For travelers approaching light speed, subjective time slows dramatically relative to the rest of the universe, creating a bizarre disconnect between the crew's experienced journey and the vast epochs passing on Earth. This effect could theoretically make even the Andromeda journey survivable for the crew, though it would come at an extraordinary cost. Time dilation emerges from the same physics that creates the speed of light barrier. As a spacecraft accelerates to higher and higher velocities, clocks aboard that ship tick progressively slower from the perspective of stationary observers back on Earth. Conversely, from the crew's perspective, their own time feels completely normal. It's the rest of the universe that appears to speed up. At everyday speeds, this effect is so minuscule as to be undetectable without atomic clocks. But at velocities approaching light speed, time dilation becomes dramatic and dominant. The mathematics are governed by the Lorentz factor, which quantifies exactly how much time slows. At 50% light speed, the Lorentz factor is about 1.15, meaning for every 1.15 years that pass on Earth, only 1 year passes for the crew. This is noticeable but not revolutionary. However, as velocity increases further, the effect becomes extreme. At 90% the speed of light, time dilation becomes profound. The Lorentz factor jumps to approximately 2.29, meaning time passes more than twice as slowly for the crew. If the spacecraft could maintain this velocity for the entire journey to Andromeda, the 2.5 million light-year distance would require about 2.78 million years as measured on Earth, accounting for the ship not quite traveling at full light speed. But for the crew aboard the ship, only about 1.2 million years would pass. Their clocks, their biology, their aging would all proceed at less than half the rate of the universe outside. This is still an impossibly long time, far beyond any human lifespan, but it represents a significant compression of experienced time. The crew would still need generation ships or suspended animation, but the subjective voyage would be measurably shorter than outside observers would measure. Push the velocity higher and the effects become even more dramatic. At 99% light speed, the Lorentz factor reaches approximately 7.09. For the crew, time passes more than 7 times slower than for Earth. The journey to Andromeda would take about 2.53 million years as measured from Earth, but the crew would experience only about 357,000 years, still a geological span, but compressed by an order of magnitude. At 99.9% light speed, the factor becomes 22.4, and crew time shrinks to roughly 112,000 years, while Earth ages 2.5 million years. At 99.99% light speed, with a Lorentz factor of about 70.7, the crew experiences approximately 35,000 years, while 2.5 million years pass in the outside universe. Each additional 9 in the percentage brings increasingly dramatic compression, though achieving these velocities becomes exponentially more difficult due to the energy requirements. The most extreme scenarios occur at velocities incredibly close to light speed. At 99.9999% of light speed, the Lorentz factor exceeds 700, and the crew would experience only about 3,500 years of subjective time for the Andromeda crossing. This begins to approach timescales that human civilizations have actually existed. At 99.999999%, 8 nines, the factor reaches about 7,000, and the journey compresses to roughly 350 years from the crew's perspective. At velocities this extreme, even our vast intergalactic gulf starts to seem potentially crossable within spans of time that, while still enormous, fall within the realm of what massive generation ships or very long-term suspended animation might theoretically handle. A crew departing Earth could, in principle, arrive at Andromeda having experienced only a few centuries of shipboard time, though Earth would have aged by millions of years. However, this creates a profound and unsettling consequence: the complete severing of temporal connection to Earth. While time dilation benefits the crew, it comes at the cost of making any return journey meaningless. If a ship travels to Andromeda at 99.99% light speed, spending 35,000 years in subjective time, and then immediately turns around and returns at the same velocity, the crew would age only 70,000 years total. But Earth would have advanced 5 million years. The civilization that launched them would be long extinct. Human evolution would have had time to work significant changes to our species. Continents would have shifted, ice ages would have come and gone, and any records or memory of the mission might have vanished entirely. The crew would be returning not to their home, but to an alien world populated by their distant descendants, if humans still existed at all. Time dilation also creates strange communication problems. Any messages sent back to Earth would arrive stretched across millions of years from Earth's perspective, while responses would take equally long to return. From the crew's perspective, if they could somehow observe Earth through a powerful telescope, they would see it speeding up like a fast-forward video, watching millions of years of planetary history unfold during their subjective decades or centuries of travel. Meanwhile, observers on Earth watching the spacecraft would see everything aboard moving in extremely slow motion, with the crew appearing nearly frozen in time. This asymmetry means the journey is fundamentally one way, not just in space, but in time. The travelers become unstuck from their own era, voyaging not just to another galaxy, but to another epoch. Even with time dilation making the journey theoretically survivable for the crew, the cost is permanent exile from everything they knew, everyone they loved, and the entire temporal context of their civilization. They would arrive at Andromeda as living fossils, ambassadors from a forgotten age. Beyond the challenges of propulsion and time, our Andromeda-bound spacecraft faces a navigation problem of staggering complexity. This isn't like plotting a course to Mars or even to a nearby star, where positions are relatively stable over mission timescales. When your journey spans millions of years, the universe itself becomes a dynamic, moving target, and every celestial object, including your destination, will have shifted dramatically by the time you arrive. Navigation at intergalactic scales requires accounting for motions so vast and complex that our spacecraft would need to aim not at where Andromeda is now, but at where it will be millions of years in the future, compensating for the movements of galaxies, stars, and the expansion of space itself. The first challenge is understanding that nothing in space is stationary. Earth orbits the Sun at 67,000 miles per hour, The Sun orbits the center of the Milky Way at roughly 514,000 miles per hour, taking about 230 million years to complete one galactic orbit. The Milky Way itself is moving through space at approximately 1.3 million miles per hour relative to the cosmic microwave background radiation, the leftover glow from the Big Bang that serves as our closest approximation to a universal reference frame. Every galaxy, every star, every object is in motion, creating a cosmos of perpetual, complex movement. Andromeda presents a particularly interesting navigation case because, unlike most distant galaxies, which are moving away from us due to cosmic expansion, Andromeda is actually approaching the Milky Way at approximately 68 miles per second, or about 244,000 miles per hour. This closing velocity exists because the gravitational attraction between our two massive galaxies overcomes the expansion of space on these local scales. In roughly 4 to 5 billion years, Andromeda and the Milky Way will collide and merge. This approach velocity actually works in our favor, slightly reducing the distance our spacecraft must travel. If we're moving toward Andromeda at, say, 10% light speed while it's simultaneously moving toward us, the closing velocity is slightly greater than our ship's speed alone, marginally reducing journey time. However, calculating a trajectory over millions of years becomes extraordinarily complex. Our spacecraft cannot simply point at where Andromeda appears in the sky and accelerate in that direction. During a 2.5 million year journey, Andromeda will have moved hundreds of thousands of light years through space along its own trajectory. The Milky Way will have moved similarly. Our spacecraft must follow an intercept course, aiming at the point in space where Andromeda will be when the ship arrives, not where it is when the ship launches. This is like shooting an arrow at a moving target from a moving platform, while both arrow and target take millions of years to complete their trajectories. The slightest miscalculation compounds into missing the destination by hundreds of thousands or even millions of light years. Complicating matters further, galaxies don't move uniformly through space. They rotate, with stars orbiting their galactic centers at different speeds, depending on their distance from the core. Andromeda rotates once approximately every 250 million years. During our journey, it will complete roughly 10 full rotations. The specific region of Andromeda we're targeting will have moved significantly around the galaxy's center multiple times. If we're aiming for a particular spiral arm or a specific star cluster, we must calculate not just where Andromeda will be as a whole, but where that specific region within the rotating galaxy will be positioned when we arrive. The gravitational influences of other nearby galaxies also affect trajectories. The local group, the cluster of galaxies that includes both the Milky Way and Andromeda, contains more than 50 galaxies. The Triangulum Galaxy, the Large and Small Magellanic Clouds, and dozens of dwarf galaxies all exert gravitational pulls that subtly alter paths through space. Over millions of years, these influences accumulate. Our spacecraft's trajectory would need to account for this gravitational choreography, calculating the cumulative effect of multiple galaxies tugging on our ship over geological timescales. Dark matter, which we'll explore later, adds another layer of complexity. Its gravitational effects are real and significant, but its distribution is difficult to map precisely. Navigation would require constant course corrections throughout the journey. Even with the most sophisticated calculations, small errors in our initial understanding of galactic positions, velocities, or masses would compound over time. The spacecraft would need autonomous navigation systems capable of measuring its position relative to galaxies, quasars, or other cosmic landmarks, comparing those observations to predicted positions and firing thrusters to adjust course. These corrections would need to occur over timescales of thousands or tens of thousands of years, with the navigation system continuously refining its understanding of where Andromeda will be and adjusting trajectory accordingly. The spacecraft essentially becomes its own autonomous explorer, making navigation decisions across time periods longer than human civilization has existed, with no possibility of receiving updated instructions from Earth due to the enormous communication delays. With our course calculated and propulsion system engaged, our spacecraft begins its long acceleration out of the solar system, a journey that serves as merely the opening act of our epic voyage. As we pass the orbit of Mars and venture into the realm of the gas giants, we encounter our first taste of the hazards that will plague the entire journey: space debris. While the solar system might seem empty, it's actually filled with countless objects, ranging from planet-sized worlds to microscopic dust grains, and at the velocities we must achieve, even the smallest particles become deadly threats. Crossing our own cosmic neighborhood reveals just how dangerous high-speed space travel becomes when kinetic energy transforms every speck of matter into a potential catastrophe. The outer solar system, beginning beyond Mars with the asteroid belt and extending through the orbits of Jupiter, Saturn, Uranus, and Neptune, contains a diminishing but still significant density of objects. As our spacecraft accelerates past Jupiter, already moving at speeds far exceeding any current space probe, we would witness the majestic giant and its retinue of moons pass by in days rather than years. But Jupiter's orbit isn't empty. The Trojan asteroids, trapped in gravitationally stable points ahead of and behind Jupiter in its orbit, number in the millions. Each represents a potential collision hazard. At conventional spacecraft velocities of tens of thousands of miles per hour, navigating through such fields requires careful planning but remains manageable. At the relativistic speeds we're targeting, potentially 10, 20, or 30% of light speed, the dynamics change completely. The relationship between velocity and kinetic energy is unforgiving. Kinetic energy equals 1/2 mass times velocity squared, meaning energy increases exponentially with speed. A grain of sand, weighing perhaps 1 milligram, colliding with our spacecraft at 10% light speed, would hit with kinetic energy equivalent to roughly 180 kilograms of TNT exploding. At 50% light speed, that same grain carries energy equivalent to 4,500 kilograms of TNT, or about 10,000 pounds of explosive. These aren't gentle bumps. They're devastating impacts that would vaporize sections of hull, destroy instruments, and potentially cripple or destroy the entire spacecraft. A particle the size of a pebble would hit with the energy of a nuclear weapon. At these velocities, even the sparse material of space becomes a minefield where every dust grain is a bullet and every pebble is a bomb. Beyond Neptune lies the Kuiper Belt, a vast region extending from about 30 to 50 astronomical units from the Sun, populated by thousands of known objects and likely billions of smaller ones. This is the realm of icy bodies like Pluto, Eris, and Makemake, remnants from the solar system's formation that never coalesced into planets. The Kuiper Belt is far less dense than the asteroid belt, but it's also much larger, and our spacecraft must traverse it while accelerating to ever higher velocities. The danger here isn't so much the large catalogued objects. We can track those and plot a course to avoid them. But the countless smaller bodies, the house-sized boulders and car-sized chunks of ice and rock that remain undiscovered and untrackable. At relativistic speeds, our spacecraft has essentially no time to detect and evade such objects. If we're traveling at 20% light speed, we cover the distance from Earth to Moon in less than 2 seconds. Anything not detected far in advance becomes unavoidable. This creates an unsolvable problem for shielding. Spacecraft designers typically protect against micrometeoroid impacts with Whipple shields, layered barriers designed to vaporize incoming particles and spread out the impact energy. But these shields work for particles hitting at kilometers per second, not at significant fractions of light speed. At relativistic velocities, even sophisticated shielding becomes inadequate. The only real defense would be massive shielding, armor so thick and heavy that it dramatically increases the spacecraft's mass, requiring exponentially more energy to accelerate and compounding all our propulsion challenges. Some designs propose using magnetic fields to deflect charged particles or clouds of plasma ahead of the ship to vaporize debris before impact. But these systems would consume enormous amounts of power and might not protect against larger, uncharged objects. The reality is that crossing the Kuiper belt at relativistic speeds means accepting risk. Our spacecraft would need to plot a course through the least dense regions, using the best available maps of large object positions, while relying on some combination of forward-looking sensors, modest shielding, and probabilistic luck to survive. The journey through our own solar system's outskirts becomes a high-stakes gamble where encountering even one object of significant size could end the mission instantly, millions of years before reaching the destination. Beyond the Kuiper belt lies the even more distant Oort cloud, a theoretical spherical shell of icy bodies extending perhaps halfway to the nearest star, though this region's density is thought to be much lower than the Kuiper belt's. Still, our spacecraft must run this gauntlet for thousands of years as it accelerates outward, every moment carrying the risk that an invisible grain of cosmic sand will strike with the force of an artillery shell, ending humanity's grandest voyage before it truly begins. After threading through the minefield of the Kuiper belt and continuing outward for years, our spacecraft eventually reaches a boundary invisible to the eye, but profound in its significance: the heliopause. This is where the Sun's influence finally fades, where the outward pressure of the solar wind, the stream of charged particles constantly flowing from our star, meets and balances against the pressure of the interstellar medium, the thin gas filling the space between stars. Crossing the heliopause, located roughly 120 astronomical units from the Sun, or about 11 billion miles, marks humanity's true departure from home. We leave behind the Sun's protective bubble and enter the realm between stars, an environment fundamentally different from anything in the solar system, and one that poses new dangers for our Andromeda-bound vessel. The heliosphere, the region of space dominated by the Sun's influence, acts as a protective cocoon for the solar system. The solar wind, traveling outward at hundreds of miles per second, creates a magnetic bubble that deflects and moderates much of the galactic cosmic radiation streaming through our region of the galaxy. This shielding isn't perfect. Cosmic rays still penetrate to Earth, which is why we need our planet's own magnetic field and thick atmosphere for additional protection. But the heliosphere significantly reduces the radiation environment compared to true interstellar space. The Voyager 1 probe crossed the heliopause in 2012, becoming humanity's first artificial object to enter interstellar space, and its instruments immediately detected a dramatic change. The density of high-energy cosmic rays increased by factors of 2 to 3. This wasn't a gradual transition, but a sharp boundary, a cosmic border crossing. For our spacecraft, crossing the heliopause means entering an environment where radiation levels are substantially higher and more dangerous. Galactic cosmic rays are high-energy particles, primarily protons, but also heavier atomic nuclei, accelerated to nearly light speed by distant supernovae, pulsar winds, and other violent cosmic events. These particles carry tremendous energy. Some reach energies millions of times greater than anything produced in human particle accelerators. When they strike matter, including spacecraft hulls or biological tissue, they cause damage at the molecular and atomic level. Electronics can suffer from single-event upsets, where a cosmic ray flips bits in computer memory or damages circuits. For any biological crew, even in suspended animation, the cumulative radiation dose over millions of years would be catastrophic without extraordinary shielding. The interstellar medium itself, while incredibly sparse by Earth standards, becomes relevant at relativistic speeds. Interstellar space contains roughly 1 atom per cubic centimetre on average, mostly hydrogen, with trace amounts of helium and heavier elements. This sounds like perfect vacuum, and by human standards it is, but at velocities approaching light speed, even this tenuous medium creates drag and bombardment. Each hydrogen atom the spacecraft encounters becomes a high-energy particle impact. At 10% light speed, striking an interstellar hydrogen atom imparts energy equivalent to the atom moving at that relativistic velocity, creating what's effectively a stream of radiation hitting the forward-facing surfaces. At higher speeds, these impacts generate secondary particles through nuclear interactions, creating cascades of radiation throughout the spacecraft structure. The faster we travel, the more intense this effect becomes, essentially transforming the thin interstellar medium into a constant radiation beam assaulting our ship. Temperature dynamics also shift dramatically beyond the heliopause. In the solar system, spacecraft designers must consider both the sun's heating and the cold of space, balancing solar panels and radiators accordingly. In interstellar space, with the sun reduced to merely the brightest star in the sky, solar heating becomes negligible. The cosmic microwave background radiation, the leftover thermal glow from the Big Bang, bathes all of space in a uniform temperature of about 2.7 Kelvin, or roughly minus 270 degrees Celsius. This is very close to absolute zero, the coldest possible temperature. Our spacecraft would need to rely entirely on internal heat generation from its power systems, and must design radiators to efficiently shed waste heat into this frigid environment. Any systems requiring warmth, whether biological life support, certain electronics, or materials that become brittle at extreme cold, would need active heating systems running continuously for millions of years. The magnetic environment changes as well. Within the heliosphere, the sun's magnetic field, carried outward by the solar wind, creates a complex but structured magnetic environment. Beyond the heliopause, our spacecraft encounters the interstellar magnetic field, which is much weaker, typically just a few microgauss compared to the heliosphere's several microgauss, but also more chaotic and variable. This field is shaped by the cumulative effect of stellar winds from countless stars, supernova remnants, and the overall galactic magnetic field. Navigating by magnetic field becomes impossible. The spacecraft must rely on stellar positions, pulsars, and other astronomical references. The change in magnetic conditions might also affect any magnetic shielding systems designed to deflect charged particles, requiring adjustments to shield configurations as we transition from solar to interstellar space. Crossing the heliopause represents more than just a physical transition. It's a psychological and philosophical threshold as well. Every human spacecraft, every human-made signal, every aspect of human activity exists within the heliosphere's protective embrace. The handful of probes that have crossed it remain connected to Earth by radio signals, still receiving commands and transmitting data back to their creators. But our Andromeda spacecraft, once it crosses this boundary and continues accelerating, begins a true separation. The sun diminishes to a point of light, indistinguishable from other bright stars except by careful measurement. Earth, even through the most powerful telescopes, would be utterly invisible, lost in the glare of its parent star. We would be truly alone in the vast dark between stars, vulnerable to cosmic radiation, navigating by the ancient light of distant suns with millions of years of journey still ahead. Beyond the heliopause, our spacecraft enters a realm of emptiness so profound that human language struggles to convey it. We talk casually, about the vacuum of space, but interstellar space reveals what true emptiness means. As the years turn to decades and then centuries, the sun fades to just another star among thousands, and our vessel finds itself in a void so vast that the nearest stellar landmark remains light years away. This is isolation on a scale that challenges comprehension, not just distance from other humans or from Earth, but separation from matter itself, from warmth, from light, from anything except the infinite dark, punctuated by distant, unreachable points of starlight. The nearest star to our Sun, Proxima Centauri, lies 4.24 light-years away, a distance of roughly 25 trillion miles. If we imagine the Sun as a basketball in New York City, Proxima Centauri would be another basketball in San Francisco, with essentially nothing but empty space between them. This represents the typical stellar separation in our region of the galaxy. Stars are separated by light years, distance so vast that even light, the fastest thing in existence, requires years to cross. Our spacecraft, even traveling at an optimistic 10% of light speed, would take 42 years just to reach Proxima Centauri. But we're not headed for Proxima Centauri. We're not even staying in our galaxy's stellar neighborhood. Our trajectory takes us through the outer regions of the Milky Way and then out into the intergalactic void, meaning we'll spend thousands upon thousands of years with no close stellar passages at all, just endless emptiness. During these millennia of flight through the void, the spacecraft's environment becomes almost abstract in its isolation. Looking forward, Andromeda would be visible as a fuzzy patch growing imperceptibly larger year by year. Looking backward, the Milky Way, our home galaxy containing everything humanity has ever known, would appear as a band of light slowly receding, the billions of stars blending into a luminous river across the sky. But looking in any other direction would reveal only darkness scattered with distant stars and galaxies, none close enough to show as anything but points of light. No planets would be visible, no asteroids, no comets, no debris fields, just the ship, alone, swimming through an ocean of nothing. The psychological weight of this isolation would be crushing for any conscious crew. Humans evolved in environments rich with sensory input. The presence of ground beneath our feet, horizons in the distance, the sounds of wind and water, the proximity of other living things. Even astronauts in Earth orbit or on the Moon can look back and see our living world, a constant reminder of home and connection. But for travelers in deep interstellar space, especially once beyond the dense stellar regions of the galaxy, there would be no such comfort. The spacecraft would become the entire universe for its inhabitants, a tiny bubble of warmth, light, and matter adrift in an infinite void. Looking out the windows would reveal only the same unchanging vista of distant starlight, no different today than yesterday or 100 years ago, no different than it will be 100 years from now. The emptiness extends beyond what we can see to what physically exists. Interstellar space, as we've discussed, contains roughly 1 atom per cubic centimeter. To put this in perspective, Earth's atmosphere at sea level contains about 25 quintillion molecules per cubic centimeter. Even the best vacuum chambers humans can create still contain billions of atoms per cubic centimeter. Interstellar space is vacuum on a level we cannot reproduce in laboratories, a void so complete that cubic meters of space might contain only a handful of atoms. Our spacecraft would be by far the densest, most complex collection of matter within light years, a lonely island of organized atoms in a sea of near-perfect vacuum. This emptiness means there's nothing to navigate by in any conventional sense. On Earth, we navigate by landmarks, mountains, rivers, roads, buildings. In the solar system, we navigate by planets, moons, and the Sun itself. But in interstellar space, there are no nearby reference points, Navigation must rely on distant objects, specific stars whose positions relative to each other change only slightly over decades, pulsars whose regular radio pulses serve as cosmic lighthouses, or even distant galaxies. The spacecraft must constantly measure angles between these distant references to determine its position and trajectory, knowing that everything, the ship, the stars, the galaxies, is all in motion together in a complex cosmic dance. Time itself would seem to stretch and distort in this emptiness. Without meaningful change in the environment, without seasons or day-night cycles unless artificially created, without the passage of planetary bodies or the shifting of constellations, time loses its markers. A year in interstellar space is no different from any other year. The same unchanging void, the same distant stars, the same isolation. For conscious beings, whether human crew or advanced AI systems, this monotony could be as challenging as the physical dangers. The mission would require either generations of people born into this emptiness, knowing nothing else, or systems capable of maintaining themselves through millennia of unchanging conditions without degradation, boredom, or despair. The vast emptiness also means that help is impossible. If something breaks, if systems fail, if an emergency occurs, the spacecraft is entirely alone. There's no rescue mission, no supply ship, no one coming to help. The nearest star system might be light years away, unreachable without decades or centuries of diversion. Earth, even if it still existed and cared about this ancient mission, couldn't send help that would arrive in any reasonable time frame. The spacecraft must be entirely self-sufficient, carrying every spare part, every resource, every capability it might ever need. This is isolation not just from people, but from civilization, from infrastructure, from the accumulated knowledge and resources of an entire species. Our vessel becomes a self-contained world, sailing through an emptiness so complete that it makes the deepest ocean trenches or the most remote deserts of Earth seem crowded and welcoming by comparison. As our spacecraft drifts through the interstellar void, one question towers above all others. How do you keep anyone or anything alive for millions of years? The time frames involved in our Andromeda journey are so vastly beyond human lifespans, or even the lifespans of civilizations, that conventional life support becomes absurd. A human lives perhaps 80 years on average. Our journey requires sustaining life across 2.5 million years, even at light speed, or potentially tens of millions of years at more realistic velocities. This isn't a problem of packing enough food and water. It's a fundamental challenge that forces us to reimagine what we mean by crew, and whether human biology can or should make this journey at all. The generation ship concept represents humanity's most romantic, but perhaps least practical answer to this challenge. Imagine a massive spacecraft, not a cramped capsule, but a flying world, large enough to house thousands of people in a self-sustaining ecosystem. The original crew launches knowing they will never see the destination. Their children won't see it either, nor their grandchildren, nor their great-great-great-grandchildren, extending down a chain of generations, numbering in the tens of thousands. If we assume 25 years per generation, a reasonable estimate for the time between parent and child, our 2.5 million year journey at light speed would span 100,000 generations. For context, all of recorded human history covers only about 200 generations. The Apollo astronauts who walked on the moon are merely 3 or 4 generations removed from us today. Asking 100,000 generations to maintain mission discipline, preserve technical knowledge, and remain committed to a goal set by ancestors who lived geological ages ago seems beyond optimistic. It seems impossible. The practical challenges of generation ships are staggering. The vessel would need a completely closed ecological system, recycling air, water, and nutrients with perfect efficiency for millions of years. Every atom would need to be reused endlessly. There's no resupply, no fresh water from Earth, no new air. Plants would produce oxygen and food, but the biological systems would need to maintain perfect balance. Too much oxygen production and the atmosphere becomes fire-prone. Too little and the crew suffocates. Waste must be completely recycled into useful nutrients. Any inefficiency, any loss of atoms to space through leaks or equipment disposal, compounds over millions of years until critical resources are depleted. The social and psychological challenges might be even more insurmountable. How do you maintain social cohesion and mission focus across 100,000 generations? Languages evolve and change. English 1,000 years ago was nearly incomprehensible to modern speakers, and that's just 40 generations. Over 100,000 generations, language would evolve, fragment, and transform beyond recognition multiple times. Culture would shift dramatically. The original mission goals, the very memory of Earth, might fade into mythology or be lost entirely. Later generations might question why they're trapped in this flying prison heading toward a destination they'll never see. Rebellion, social collapse, or simple loss of mission focus could end the journey at any point. The ship would need governance systems stable enough to last longer than any empire in human history, maintaining order and purpose across timescales during which entire civilizations on Earth rose and fell. Cryogenic suspension offers a tempting alternative. Simply freeze the crew and wake them upon arrival. The biological processes that lead to aging and death are temperature-dependent chemical reactions. Slow them enough by cooling the body, and you could theoretically preserve a person indefinitely. However, current cryogenic technology is crude at best. We can freeze and revive simple organisms and some tissues, but freezing a whole human causes ice crystals to form in cells, rupturing cell membranes and destroying tissue structure. Vitrification, turning tissue into a glass-like solid without ice crystal formation, shows promise but requires careful control and still causes some damage. Even if we solve the technical problem of freezing and reviving humans perfectly, maintaining a cryogenic system for millions of years presents enormous challenges. The storage chambers require constant cooling, meaning constant power generation. Any failure in the cooling system, even briefly, could cause partial thawing and irreversible damage. The spacecraft needs to monitor the frozen crew continuously and perform maintenance on the cryogenic systems for millions of years, requiring either incredibly reliable automated systems or some crew members remaining awake in rotation, which brings us back to life support problems. Digital consciousness transfer represents perhaps the most speculative option, uploading human minds into computer systems that could theoretically run for millions of years. If consciousness is ultimately information processing, and if we could map and simulate a human brain in sufficient detail, then the crew could exist as software, experiencing virtual environments while the physical ship flies itself. Digital beings wouldn't need food, water, or air. They could be paused during uneventful periods and resumed when needed. Multiple copies could exist for redundancy. Time could even be artificially accelerated or slowed in their simulations. The crew might experience only years or days, while millions of years pass outside. However, this requires technologies and understanding we don't currently possess. We can't yet map a complete human brain at the necessary resolution, can't simulate brain chemistry at the required scale, and have no idea if such a simulation would actually produce consciousness or just an elaborate imitation. The philosophical questions alone are daunting. Would the uploaded copy really be you, or just a duplicate while the original dies? Would digital existence even be recognizable as human experience? These problems lead many scientists to conclude that any realistic Andromeda mission wouldn't carry biological humans or even uploaded human minds, but rather artificial intelligence. Sophisticated machines designed specifically for this journey. An AI probe wouldn't need life support, wouldn't age biologically, and could be designed with redundant systems and self-repair capabilities. It could spend most of the journey in low power mode, awakening periodically to check systems and navigate. Upon reaching Andromeda, it could conduct scientific observations, collect data, and perhaps even transmit findings back to Earth, though the 2.5 million year signal delay makes even that gesture mostly symbolic. An AI probe sidesteps the impossible biology problems but raises its own questions. What counts as a successful mission if no human experiences it? Is sending a robot to Andromeda meaningful exploration or just expensive data collection? And can we create AI systems reliable and sophisticated enough to operate independently for millions of years, maintaining mission focus without human guidance? Whether our Andromeda spacecraft carries biological humans, digital consciousness, or purely artificial intelligence, it must survive one of space's most relentless threats: radiation. In deep space, far from Earth's protective embrace, our vessel would face a constant bombardment of high-energy particles that could degrade electronics, destroy biological tissue, and slowly but inevitably damage any material over the millions of years of flight. Understanding this radiation environment and designing protection against it represents one of the mission's most fundamental engineering challenges, one where perfect solutions may simply not exist. On Earth, we live shielded beneath layers of protection we rarely consider. Our planet's magnetic field, generated by churning molten iron in the core, extends tens of thousands of miles into space, creating the magnetosphere, an invisible force field that deflects most charged particles coming from the Sun and deep space. Solar wind particles, which would otherwise strip away our atmosphere and irradiate the surface, are channeled toward the magnetic poles, where they create the aurora borealis and australis, but cause little harm. Earth's atmosphere provides a second layer of defense, equivalent to about 10 meters of water in terms of shielding capability. Cosmic rays that penetrate the magnetosphere collide with atmospheric molecules, creating cascades of secondary particles that mostly dissipate before reaching the ground. Together, these shields reduce surface radiation to levels where life can flourish. Even at cruising altitude for commercial aircraft, radiation levels are only modestly elevated. Astronauts on the International Space Station, though above most of the atmosphere, still benefit from Earth's magnetic field and receive radiation doses that are elevated but manageable for missions lasting months. In deep interstellar space, all these protections vanish. The Sun's magnetic influence fades beyond the heliopause. No planetary magnetic field exists to deflect particles. There's no atmosphere to absorb and scatter radiation. Our spacecraft becomes naked to the cosmos, exposed to the full fury of galactic cosmic rays, high-energy particles, primarily protons, but including heavier nuclei like helium, carbon, and iron, accelerated to nearly light speed by supernovae and other violent events scattered throughout the galaxy. These particles carry tremendous energy, often measured in giga-electron volts or even tera-electron volts, billions or trillions of electron volts. When they strike matter, they penetrate deeply, causing ionization damage and nuclear reactions. A single cosmic ray can pass through meters of solid material, creating a trail of destruction through whatever it encounters. For biological tissue, cosmic ray damage is devastating. High-energy particles break chemical bonds, damage DNA, destroy cells, and create cascading secondary reactions. A human exposed to the deep space radiation environment without shielding would receive a lethal dose within days or weeks. Even with shielding, the cumulative dose over years becomes problematic, dramatically increasing cancer risk and causing other radiation-related illnesses. For a generation ship with thousands of people living over millions of years, radiation would be a constant health crisis unless extraordinary shielding was implemented. For cryogenically frozen humans, radiation damage would accumulate in the suspended tissue, potentially causing problems upon revival, even if the freezing and thawing process worked perfectly. Electronics also suffer from radiation. Cosmic rays can cause single-event effects. A particle striking a computer chip can flip bits in memory, causing errors, or damage transistors, causing permanent failure. Modern spacecraft use radiation-hardened electronics, but these are merely more resistant, not invulnerable. Over millions of years, the accumulated damage from cosmic ray impacts would gradually degrade any electronic system. Computer memory would develop errors, processors would malfunction, and eventually systems would fail unless constantly repaired or replaced. An AI-controlled probe would need massive redundancy, multiple independent computer systems, constant error checking and correction, and the ability to fabricate replacement components from stored materials. Shielding against cosmic rays is difficult because the particles are so energetic. Traditional radiation shielding uses dense materials like lead to absorb gamma rays and other electromagnetic radiation, but cosmic rays are far more penetrating. Paradoxically, very dense shielding can actually make things worse for the highest energy particles. When a cosmic ray strikes a heavy nucleus like lead, it can create a shower of secondary particles through nuclear fragmentation, resulting in more radiation inside the shielded area than outside. More effective shielding uses lighter materials with high hydrogen content, like water, plastics, or liquid hydrogen, which slow and absorb particles through many small interactions rather than creating dangerous secondaries. Some designs propose using water as shielding, surrounding habitable areas with tanks of water several meters thick, which provides both radiation protection and a useful resource. Others suggest using the spacecraft's fuel supply, whether liquid hydrogen for fusion or other materials, as shielding during the journey, though this only works during phases when substantial fuel remains aboard. More exotic proposals include magnetic shielding, generating artificial magnetic fields around the spacecraft to deflect charged particles, mimicking Earth's magnetosphere on a smaller scale. This requires enormous amounts of power to generate field strengths sufficient for protection, and it only works against charged particles, offering no defense against neutral particles or electromagnetic radiation. The harsh reality is that perfect shielding for a million-year journey may be impossible with any conceivable technology. Every material degrades over time, developing cracks, losing structural integrity, or being slowly eroded by the very radiation it's meant to block. Maintaining meters-thick shielding around a spacecraft adds enormous mass, compounding our propulsion challenges. The best practical approach might be a combination of modest physical shielding, magnetic deflection for charged particles, strategic positioning of critical systems in the most protected areas, massive redundancy in all electronics, and accepting that biological crew simply cannot survive such exposure. This final conclusion, that biology and multi-million-year space journeys are fundamentally incompatible, represents perhaps the most profound limitation facing our Andromeda mission, suggesting that if this journey is ever attempted, it will be by machines designed to withstand what no living thing could endure. As radiation batters our spacecraft and the years stretch into centuries, another form of isolation sets in, one perhaps even more profound than physical distance. Communication with Earth, that final thread connecting our voyages to home, begins to fray and eventually snaps entirely. The speed of light, which limits our spacecraft's velocity, also constrains how fast information can travel, and over the vast distances to Andromeda, communication transforms from conversation into something closer to launching messages in bottles across an ocean of time. Radio waves, which carry our communications, travel at light speed. When our spacecraft is near Mars, radio signals take about 20 minutes to reach Earth. Annoying, but manageable. Mission Control sends a command, waits 20 minutes for it to arrive, then waits another 20 minutes for the spacecraft's response. By the time Voyager 1 reached the edge of the solar system, about 14 billion miles away, signals took roughly 21 hours each way, a full-day conversation delay. But these delays, frustrating as they are, still allow meaningful communication. You can send a question to Voyager today and receive an answer tomorrow. For our Andromeda mission, communication rapidly becomes absurd. When the spacecraft reaches just 1 light-year from Earth, a tiny fraction of the journey, signals take a full year to travel each way. Send a message today, and if anyone responds immediately upon receiving it, you won't hear back for 2 years. By the time the ship reaches 10 light-years out, barely having left our immediate stellar neighborhood, any exchange takes 20 years. A question asked by a mission controller would receive an answer when that controller is approaching retirement, sent by a spacecraft that left when they were young. By 100 light-years, still well within the Milky Way, communication becomes multi-generational. The people who received the spacecraft's transmission weren't born when it was sent. As the spacecraft ventures into the thousands and then millions of light-years, communication ceases to have any practical meaning. At 10,000 light-years, one-way transmission takes 10,000 years, longer than human civilization has existed. Any message sent from the spacecraft would arrive on Earth 10,000 years in the future, where it would be received by humans so culturally and perhaps even biologically different from us that they might not recognize it as a message from their ancestors. By the time the ship reaches Andromeda's distance, any signal transmitted takes 2.5 million years to arrive. If the crew sent a message saying, "We have arrived," and if Earth immediately responded with, "Congratulations," that response would reach the spacecraft 5 million years after their arrival. In that time, entire species can evolve and go extinct. The psychological weight of this isolation is difficult to overstate. Early in the mission, the crew might still send messages home, maintaining the ritual of communication even as the delays stretch to decades. They might receive responses from Earth, carefully preserved messages from mission control, updates on human civilization, perhaps recorded greetings from family members, knowing these would be the last words their descendants would receive. But inevitably, the delays would grow too long. Eventually, no one aboard the ship would have any living connection to anyone on Earth. The people sending messages from Earth wouldn't be anyone the crew knew, possibly not even speaking recognizable languages. Earth's transmissions might stop entirely. Perhaps the civilization ended, or simply decided the futile exercise of shouting across millions of years no longer served any purpose. This communication breakdown means the spacecraft operates in complete autonomy for almost the entire journey. Any problem that develops must be solved by the crew or onboard systems without Earth's help. There are no software updates from mission control, no instructions on how to handle unexpected situations, no encouragement from home when morale falters. If something breaks in a way the designers didn't anticipate, the crew must improvise solutions with only the resources aboard. Every decision becomes final and irreversible. There's no consulting with experts on Earth, no democratic input from humanity, no wisdom from the civilization that launched the mission. The isolation extends beyond practical concerns to existential ones. For conscious beings aboard, whether biological humans or artificial intelligence, the knowledge that you are utterly, completely alone, that no help can possibly come, that you could die and no one would know for millions of years, creates a psychological environment unlike anything humans have experienced. Even the most remote Antarctic research stations maintain radio contact with civilization. Even astronauts on the Moon could talk to Earth with only a few seconds delay. But our Andromeda travelers would exist in a silence broken only by their own voices and the cold electromagnetic whisper of distant stars. Perhaps most unsettling is the possibility of receiving messages long after their context has vanished. Imagine the spacecraft receiving a transmission from Earth sent thousands of years ago, discussing events, people, and concerns long since turned to dust. Or receiving a final message, Earth's last transmission before some catastrophe, war, or simply the decision to stop broadcasting, and knowing that by the time you received it, whatever happened concluded millennia ago. The spacecraft might spend millions of years replaying ancient messages from a world that no longer exists, a one-way conversation with ghosts across an unbridgeable gulf of time and space. As our spacecraft continues its relentless journey, having spent tens or hundreds of thousands of years crossing through the Milky Way's outer regions, it eventually reaches a transition even more profound than leaving the solar system, the boundary between galaxies. Here, in the middle section of our voyage, we enter the intergalactic void, a realm of emptiness so complete that interstellar space seems crowded by comparison. This is the gulf between island universes, where even the sparse hydrogen atoms of interstellar space become vanishingly rare, and the isolation reaches its absolute peak. The Milky Way and Andromeda aren't alone in space, but are part of what astronomers call the local group, a gravitationally bound collection of more than 50 galaxies spanning roughly 10 million light-years. The Milky Way and Andromeda dominate this group, being the two largest spiral galaxies, each containing hundreds of billions of stars. Andromeda, the larger of the two, holds perhaps 1 trillion stars and spans 220,000 light-years in diameter. The Milky Way, slightly smaller, with 200 to 400 billion stars, stretches about 100,000 light-years across. Together, these two giants account for most of the local group's total mass, with dozens of smaller dwarf galaxies orbiting around them like moons around planets. The large and small Magellanic Clouds, visible from Earth's southern hemisphere, are examples of such satellite galaxies orbiting the Milky Way. The space between these galaxies represents emptiness on a scale difficult to comprehend. While interstellar space within a galaxy contains roughly 1 atom per cubic centimeter, intergalactic space holds perhaps 1 atom per cubic meter, or even less, a 1,000-fold decrease in density. This is vacuum approaching the theoretical limit of emptiness, void so complete that cubic kilometers might contain only handfuls of atoms. If interstellar space is a desert, intergalactic space is the void between planets, not just empty of landmarks, but empty of matter itself at any scale we can easily imagine. For our spacecraft crossing this gulf, the experience would be one of almost abstract isolation. Looking back, the Milky Way would appear as it does to us when we observe Andromeda, a faint, fuzzy spiral smeared across a small patch of sky, its billions of stars blending into a ghostly glow. Individual stars would be completely invisible, too distant for even the brightest to resolve as anything but contributors to the galaxy's overall luminescence. Looking forward, Andromeda would similarly appear as a growing patch of light, its spiral structure gradually becoming more distinct, but still appearing as an ethereal cloud rather than individual stars. In every other direction, darkness punctuated by distant galaxies, each appearing as faint smudges, and the cold scatter of background starlight from billions of light-years away. The spacecraft would spend perhaps 1 million years or more crossing this intergalactic desert, depending on its velocity. During this time, there would be essentially nothing nearby. No stars within light-years, no dust clouds, no planets, no comets, nothing but the ship itself and the thinly scattered atoms of the intergalactic medium. Even the background radiation would be minimal. The cosmic microwave background would still bathe the spacecraft in its 2.7 Kelvin glow, but there would be no stellar radiation warming one side of the vessel, no nearby stars to navigate by, nothing to mark the passage of time except the slow, imperceptible growth of Andromeda ahead and recession of the Milky Way behind. This emptiness offers one advantage. The danger from debris nearly vanishes. While interstellar space within galaxies contains dust and occasional larger particles that pose collision risks at relativistic speeds, intergalactic space is so empty that the probability of striking anything becomes astronomically small. The spacecraft could cruise through this void with minimal risk of impact, though the cosmic ray radiation continues unabated. Those high-energy particles originate from throughout the universe and permeate even the emptiest voids. Psychologically, for any conscious beings aboard, this middle section might be the most challenging. In the Milky Way, at least there were stars, even if distant. Approaching Andromeda, there would be the growing anticipation of arrival, the destination becoming ever more real. But in the intergalactic void, there is only absence. No landmarks, no change, no sense of progress except abstract calculations of distance remaining. This is where the journey's immensity becomes most apparent, where travelers would confront the full reality of the gulf between galaxies. The spacecraft becomes a mote of organized matter in an ocean of nothing. Its tiny spark of warmth and complexity surrounded by cold vacuum stretching for hundreds of thousands of light years in every direction. The intergalactic medium itself, though nearly empty, holds mysteries. Dark matter, the invisible substance that makes up most of the universe's mass, exists here. Its gravitational effects measurable even if the matter itself remains undetectable by conventional means. The spacecraft would be traveling through this dark matter, experiencing its gravitational influence, yet unable to see or directly measure it. As our spacecraft drifts through the intergalactic void, it moves not just through empty space, but through an invisible ocean of dark matter, a mysterious substance that makes up roughly 85% of all matter in the universe, yet remains completely invisible to our instruments. This ghostly material, along with the strange gravitational currents it creates, shapes the motion of galaxies and would subtly but significantly affect our spacecraft's trajectory. Understanding and accounting for these invisible forces represents one of navigation's most peculiar challenges, plotting a course through a universe where most of the mass is fundamentally undetectable. Dark matter reveals itself only through gravity. Astronomers first suspected its existence when they observed that galaxies rotate too fast. Stars in the outer regions orbit the galactic center at speeds that should fling them into space if only the visible matter existed. The observed stars, gas, and dust simply don't provide enough gravitational pull to hold galaxies together at their observed rotation rates. Something invisible must be present, providing the additional gravity needed to explain what we see. Observations of galaxy clusters, gravitational lensing where light bends around massive objects, and the structure of the cosmic microwave background all confirm that dark matter exists in vast quantities, outweighing normal matter by about 5 to 1. What dark matter actually is remains one of physics' greatest mysteries. It doesn't emit, absorb, or reflect light or any other electromagnetic radiation. It's completely transparent and invisible. It doesn't interact with normal matter through electromagnetic or strong nuclear forces, only through gravity and possibly the weak nuclear force. Various candidates have been proposed. Exotic particles like WIMPs, weakly interacting massive particles, axions, or sterile neutrinos. But despite decades of experiments, dark matter has never been directly detected. We know it's there because of what it does gravitationally, but we can't see it, touch it, or measure it directly. For our Andromeda mission, dark matter's gravitational influence cannot be ignored. Dark matter forms massive halos around galaxies, extending far beyond the visible stars and gas. The Milky Way's dark matter halo likely extends hundreds of thousands of light-years well beyond the visible disk. Andromeda has its own dark matter halo. Between galaxies, dark matter forms vast cosmic web structures, filaments, and sheets spanning millions of light-years. As our spacecraft travels, it moves through these invisible structures, experiencing their gravitational pull. The trajectory must account for this unseen mass, or the ship could drift off course by thousands or millions of light-years over the journey's duration. The challenge is that mapping dark matter distribution is indirect and imprecise. We can infer its presence from galaxy rotation curves, from gravitational lensing observations where dark matter's gravity bends light from more distant objects, and from computer simulations of cosmic structure formation. But these methods give us only approximate distributions at large scales. We don't have detailed maps showing exactly where dark matter concentrations exist along our flight path. Navigation systems would need to continuously observe the motion of visible galaxies and stars, using their velocities and positions to infer the dark matter distribution, then calculate gravitational effects on the spacecraft's trajectory. Adding to navigation complexity is the fact that galaxies aren't just moving randomly, they're caught in large-scale gravitational flows. Our local group is being pulled toward what astronomers call the Great Attractor, a massive concentration of mass hundreds of millions of light-years away in the direction of the Hydra and Centaurus constellations. Beyond that lies an even larger structure called the Shapley supercluster. These distant mass concentrations exert gravitational pull on everything in our cosmic neighborhood, including the Milky Way, Andromeda, and our spacecraft. The motion of our local group isn't determined just by the mutual attraction of the Milky Way and Andromeda, but by this vast gravitational landscape shaped largely by invisible dark matter. Our spacecraft would need to account for these large-scale flows. While the Great Attractor's influence on our specific trajectory to Andromeda might be small, we're not traveling toward it directly. Gravitational effects from massive structures hundreds of millions of light-years away do contribute to the overall gravitational field through which we travel. Over millions of years, even tiny gravitational influences compound into significant trajectory deviations. The navigation system would essentially need to continuously solve the multi-body gravitational problem for the entire local group and beyond, accounting for both visible and inferred dark matter distributions, updating calculations as new observations refine our understanding of mass distribution. Interestingly, dark matter might actually help in some ways. If we could better understand dark matter's distribution, it could serve as a navigation aid, the invisible scaffolding of the cosmos providing gravitational landmarks. The spacecraft might measure how galaxies are moving, deduce local dark matter density, and use this information to verify its position and trajectory. Dark matter's gravitational lensing effects on light from distant galaxies could provide another navigation method, allowing the spacecraft to essentially map the invisible mass around it by observing how background light distorts. After millions of years crossing the intergalactic void, our spacecraft finally begins to approach its destination, and Andromeda transforms before the instrument's gaze. What started as a faint smudge, indistinguishable from countless other distant galaxies, slowly, imperceptibly at first, begins to grow and resolve into structure. This is perhaps the only reward for our impossible journey, the view as we draw near to another galaxy, seeing what no human eye has ever witnessed, the magnificent architecture of a spiral galaxy from close range, its beauty emerging detail by detail from the cosmic fog. From Earth, Andromeda appears as an elongated fuzzy patch about 6 times the width of the full moon. visible to the naked eye under dark skies, but revealing little detail without telescopes. Even through powerful telescopes, we see it as a flat image, a two-dimensional projection of a three-dimensional structure. But as our spacecraft approaches, Andromeda would begin to show depth, dimension, and increasingly fine detail. At perhaps 500,000 light-years out, 1/5 of the total journey, the galaxy would still appear relatively small but would have grown noticeably, its spiral structure becoming apparent. The characteristic shape would emerge, a bright, concentrated central bulge surrounded by a flatter disk traced by graceful spiral arms curving outward into space. The central bulge, home to older, redder stars packed densely together, would glow with steady, yellowish light. This spheroidal concentration contains perhaps 100 billion stars crammed into a region only a few thousand light-years across, far denser than the stellar neighborhoods in our Sun's region of the Milky Way. As we approach closer, this bulge would dominate the view, growing from a bright spot into a blazing core of starlight. Unlike the spiral arms with their distinct structure, the bulge appears as a smooth, continuous glow. Individual stars too numerous and distant to resolve separately, their combined light creating an almost solid-seeming sphere of luminosity. The spiral arms, by contrast, would reveal themselves as structured, elegant sweeps traced by brilliant blue regions and dark lanes. These arms aren't solid structures, but density waves, regions where gas, dust, and stars bunch up temporarily as they orbit the galactic center at different speeds. The blue regions mark areas of active star formation, where massive, hot young stars blaze intensely with short lifetimes measured in millions rather than billions of years. These blue giants, scattered along the spiral arms like jewels on a string, would become individually distinguishable as we draw nearer, each one a sun far more massive and luminous than our own. Between and around them, reddish regions would appear, nebulae where gas and dust glow from the radiation of nearby stars, stellar nurseries where new stars are being born even now. The dark lanes tracing the spiral arm's inner edges would also become apparent. These are dust clouds, vast concentrations of microscopic particles that absorb and scatter light from stars behind them. From our external vantage point approaching the galaxy, these dust lanes would appear as dark ribbons winding through the spiral structure, creating contrast and definition. Where within the Milky Way these dust clouds block our view of much of our own galaxy, here we would see them as features adding to Andromeda's beauty, dark threads woven through the tapestry of starlight. At perhaps 100,000 light-years out, Andromeda would fill a significant portion of the sky, its spiral structure obvious and glorious. The spacecraft would observe features that Earth-bound telescopes can only barely distinguish. Individual globular clusters, the ancient spherical collections of hundreds of thousands of old stars that orbit in the galaxy's halo. Satellite dwarf galaxies gravitationally bound to Andromeda. Perhaps even the supergiant stars, objects so luminous they outshine entire star clusters. The galaxy would no longer appear as a single object, but as a complex system, a civilization of stars, each one a sun potentially with its own planets, each arm a distinct region with its own character and history. Closer still, at tens of thousands of light-years, individual bright stars would become distinguishable across the galaxy's face. The smooth glow would fragment into countless points of light, though the sheer number, approaching 1 trillion stars, means that even from this reduced distance, much of the galaxy would still appear as a luminous haze, too many stars too close together to separate. The view would be simultaneously overwhelming and sublime, a galaxy no longer distant and abstract but immediate and real, a vast stellar metropolis stretching across hundreds of thousands of light-years, home to more stars than humans can count, more worlds than we can imagine. The spacecraft would need to decide on a specific destination within this immensity. Andromeda isn't a single place, but an entire galaxy. And choosing where to go becomes the final navigation challenge, toward the dense core, the active spiral arms, or the quieter outer regions. Each choice offers different scientific opportunities and different hazards. As Andromeda fills the sky before us, growing from a magnificent distant spectacle into an immediate presence, our spacecraft faces perhaps its greatest technical challenge yet: slowing down. After spending perhaps hundreds of thousands of years accelerating to relativistic speeds and then cruising through the void at a significant fraction of light speed, we must now somehow brake, shedding enormous kinetic energy to avoid simply shooting through Andromeda and out the other side. The deceleration problem proves just as difficult, if not more so, than the initial acceleration, and it must begin long before we reach the galaxy's visible edge. Andromeda's gravitational influence extends far beyond its visible stars. The galaxy's dark matter halo, that invisible mass we discussed earlier, creates a gravitational well stretching hundreds of thousands of light years into space. Our spacecraft would first encounter this influence perhaps 500,000 light years out, feeling a subtle tug that grows steadily stronger as we approach. But this gravity, while significant on cosmic scales, is far too weak to slow our relativistic spacecraft appreciably. Gravity might help slightly, allowing what's called gravitational capture if our velocity is low enough, but at 10, 20, or 30% of light speed, we're moving far too fast for Andromeda's gravity to capture us. We would need active braking, and lots of it. The deceleration challenge mirrors the acceleration problem, but with a cruel twist. We must carry the fuel or mechanism needed for braking throughout the entire journey, adding mass that had to be accelerated in the first place. For a rocket-based system, this means carrying propellant for deceleration from the very beginning, making the initial acceleration even more difficult. One proposed solution is a two-stage mission. Use a powerful laser array or magnetic launcher back in the Milky Way to accelerate the spacecraft using a solar sail, carrying minimal fuel on board, then flip the sail around to brake against Andromeda's starlight as we approach. But Andromeda's light is much weaker until we're very close, making this inefficient. Another option is to deploy a massive drag sail, a huge, thin membrane that catches the sparse atoms of the intergalactic and then galactic medium, using friction to gradually slow down over tens of thousands of years. More exotic proposals include magnetic scoops, generating powerful magnetic fields to catch interstellar hydrogen and helium, using them either as fuel for ongoing propulsion or simply as reaction mass to brake against. As we enter Andromeda's outer halo, the density of gas increases slightly from the near vacuum of intergalactic space, providing more material to work with. But even in the galactic halo, densities remain incredibly low, perhaps 10 to 100 atoms per cubic centimeter, making this a gradual process requiring enormous collection areas and long timescales. The spacecraft might need to begin deceleration maneuvers 100,000 or even 200,000 light-years before reaching its final destination, dedicating the final hundreds of thousands of years of the journey to slowing down. As we enter Andromeda's halo region, we would encounter the galaxy's globular clusters, ancient stellar cities orbiting far from the galactic disk. These spherical collections of stars, each containing hundreds of thousands to millions of stars, packed into regions just tens of light years across, orbit through the halo in elliptical paths that take them far above and below the main galactic plane. Andromeda hosts an estimated 450 to 500 of these globular clusters, compared to about 150 in the Milky Way. They appear as compact, bright knots of light. They're stars so old that they've burned with steady, reddish light for 10 billion years or more, nearly as old as the universe itself. Passing near a globular cluster would offer spectacular views. Thousands of stars visible simultaneously, their combined light creating a glow visible from vast distances. Unlike the loose stellar arrangements we're familiar with in our solar neighborhood, where the nearest star is light years away, in a globular cluster's core, stars are separated by mere light days or light weeks, close enough that their night skies would blaze with thousands of bright stars, and gravitational interactions between stars would be common. Our spacecraft would need to navigate carefully to avoid these dense stellar concentrations, as passing through a globular cluster at relativistic speeds would dramatically increase collision risk with stars, planets, or debris. The outer halo also contains scattered individual stars, old stars on highly elliptical orbits, population 2 stars as astronomers call them, metal poor and ancient. These stars represent some of Andromeda's oldest stellar citizens, born in the galaxy's early history when it contained less of the heavier elements forged in previous generations of stars. Their presence marks our transition from intergalactic space to galactic space, from the void between island universes to the populated regions of a new galaxy. As deceleration continues and we penetrate deeper into Andromeda's gravitational embrace, the stellar density would increase. What was empty void becomes sparsely populated space, then regions where stars become visible individually at distances of hundreds or tens of light years. Our instruments would begin detecting planets around nearby stars, observing stellar systems in detail for the first time since leaving the Milky Way millions of years ago. Having successfully decelerated and entered Andromeda's embrace, our spacecraft now faces an embarrassment of riches. Where exactly do we go in a galaxy containing 1 trillion stars? Andromeda isn't a single destination, but a vast, structured stellar civilization with distinct regions, each offering different characteristics, opportunities, and hazards. Understanding the galaxy's architecture becomes crucial as we navigate through this immense stellar metropolis, choosing our path through neighborhoods ranging from sparse, ancient stellar suburbs to dense, active stellar downtowns blazing with the light of newborn suns. The halo, which we've already begun traversing, forms the galaxy's outermost region, a roughly spherical volume extending perhaps 300,000 light-years from the galactic center. This is the domain of the old and the sparse, ancient stars, globular clusters, and streams of stars torn from satellite galaxies that Andromeda has gravitationally shredded over billions of years. Stellar density here is extremely low, with vast distances between individual stars. The halo contains relatively little gas or dust, meaning essentially no new stars form here. It's a retirement community of the cosmos, populated by stars born when the universe was young. For our spacecraft, the halo offers safe, uncrowded space for final approach maneuvers, but scientifically, it's perhaps the least interesting region. These old, metal-poor stars tell us about the galaxy's ancient past, but offer little in terms of active stellar processes or the potential for life-bearing planets. The disk is where Andromeda's main action occurs, a flattened, rotating structure about 220,000 light-years across, but only a few thousand light-years thick. This is analogous to the Milky Way's disk where our Sun resides, and it contains most of Andromeda's normal matter, stars, gas, dust, and presumably planets. The disk itself has structure. It's not uniform, but organized into spiral arms traced by bright blue stars and reddish nebulae. Stellar density in the disk varies by location, but averages much higher than the halo, with stars typically separated by a few light-years rather than tens or hundreds. This is populated space on a galactic scale, regions where stars are numerous enough that our spacecraft would rarely travel far without passing relatively near another stellar system. The spiral arms represent the disk's most visually striking and scientifically interesting features. These aren't fixed structures, but density waves, regions where stars, gas, and dust temporarily bunch up as they orbit at different speeds. The inner regions of Andromeda rotate faster than the outer regions, causing material to periodically pile up and then disperse, creating the spiral pattern. The arms mark regions of active star formation, where giant molecular clouds collapse under their own gravity to birth new stars. Massive, hot blue stars, the type O and B supergiants that live fast and die young, blaze along the spiral arms, their intense radiation lighting up surrounding nebulae and triggering further star formation in nearby clouds. These regions would be spectacular to observe. Stellar nurseries glowing pink and red from ionized hydrogen, dark dust lanes contrasting with blazing young star clusters, and the occasional supernova as a massive star exhausts its fuel and explodes. However, the spiral arms also present hazards. Higher stellar density means increased collision risk if we're still moving at significant velocity. The active star formation means supernovae occur more frequently here than in quieter regions, each explosion releasing energy equivalent to the Sun's entire lifetime output in mere days and flooding surrounding space with deadly radiation and high-velocity debris. The abundant gas and dust, while beautiful, creates navigation challenges and potential drag on the spacecraft. Dense molecular clouds could slow us or cause heating from friction if we pass through them at high speed. The central bulge represents the galaxy's ancient heart, a roughly spherical or ellipsoidal concentration of stars dominating the innermost 10,000 light-years or so. Here, stellar density reaches levels unimaginable in our Sun's neighborhood. In the bulge's core, stars might be separated by mere light weeks or even light days, packed so densely that their gravitational interactions become significant. Stellar collisions, while still rare on human timescales, are far more common here than in the disk. The bulge stars are predominantly old and red, similar to halo stars, but packed into a much smaller volume. This creates a region glowing with steady golden light, millions of suns crowded together, their combined luminosity creating one of the brightest regions in the local group. At the very center of Andromeda, like essentially all large galaxies, lurks a supermassive black hole. This one containing approximately 100 to 200 million solar masses, making it significantly more massive than the Milky Way's central black hole. The region within a few light-years of this monster is a violent place, with stars orbiting at tremendous velocities, occasional stars being torn apart by tidal forces, and energetic radiation from material falling into the black hole. This innermost region, while scientifically fascinating, would be extraordinarily dangerous for our spacecraft. The intense radiation, high stellar velocities, and strong gravitational gradients create an environment hostile to exploration. Choosing a destination means weighing these factors. The spiral arms offer the most active dynamic environments and the best chances of finding younger planetary systems that might harbor life, but come with higher hazards. The outer disk provides safer conditions while still offering interesting stellar populations. The bulge promises unique observations of dense stellar environments, but limited prospects for finding planets suitable for life. Our spacecraft must make a choice that no human mission has ever faced, selecting not just a star system, but an entire galactic neighborhood to call our destination. After examining the staggering technical challenges, the impossible timescales, and the profound isolation of this journey, we must confront a fundamental question. Why would humanity ever attempt such a mission? What purpose could possibly justify spending the resources of an entire civilization to send something, whether human, artificial intelligence, or probe, on a voyage that will outlast empires, species, and perhaps even the memory of its own launch? The answer reveals something essential about what it means to be human. about the drives that push us beyond the comfortable and known into the hostile unknown, even when practical justification seems absurd. The search for life beyond Earth stands as perhaps the most scientifically compelling motivation. Despite decades of searching, we remain alone in the cosmos as far as we can confirm. We've found no radio signals from alien civilizations, no evidence of technological activity beyond Earth, no confirmed biosignatures in exoplanet atmospheres. The question, "Are we alone?" remains unanswered, and Andromeda, with its trillion stars and presumably quadrillions of planets, represents an entirely unexplored frontier. If life exists elsewhere in the universe, another galaxy offers opportunities to find it that our own galaxy doesn't. A completely independent sample, evolved in isolation from whatever happened in the Milky Way. Finding life, even microbial life, in Andromeda would prove that biology isn't a cosmic accident, but a natural outcome of chemistry and physics, suggesting the universe teems with life. Finding intelligent life would be even more profound, confirming we're not the cosmos's sole conscious observers. But we must ask, would this discovery justify the mission's cost? Would confirmation that we're not alone change humanity's trajectory enough to warrant such an investment? Alternatively, the mission might serve as an archive, a preservation of human knowledge and culture sent beyond our galaxy as insurance against extinction. Earth faces existential risks, asteroid impacts, supervolcanic eruptions, climate change, nuclear war, or threats we haven't imagined. Even the Milky Way isn't permanent. The Sun will eventually die, and the collision with Andromeda, while billions of years away, will dramatically alter both galaxies. Sending a spacecraft to Andromeda with a complete record of human civilization, our art, science, history, DNA, and culture, would create a backup copy of humanity stored in a different galaxy. If Earth, or even the entire Milky Way, faced catastrophe, this archive might survive. It's a message in a bottle cast into the cosmic ocean, hoping that someone, somewhere, sometime might find it, and know that we existed, that we created, that we mattered. But this motivation feels melancholic, almost desperate, building a tomb rather than a future, accepting defeat rather than solving our problems at home. The drive to explore offers perhaps the most honest motivation, though the hardest to justify economically. Humans have always pushed boundaries, climbed every mountain, crossed every ocean, ventured to both poles and into space itself, often for no practical reason beyond because it's there. This exploratory impulse seems hardwired into our species. The same curiosity that led our ancestors out of Africa now pulls us toward the stars. Reaching Andromeda would represent the ultimate expression of this drive, the farthest possible journey, touching another island universe separated from ours by millions of light years of void. The mission succeeds not by finding anything specific, but simply by going, by proving it possible, by extending humanity's reach across intergalactic space. We go not for profit or safety, but because remaining forever confined to one galaxy feels like living in a single room when infinite mansions lie beyond the door. Yet we must honestly confront whether any of these justifications hold up against scrutiny. The resources required, the energy of millions of nuclear weapons to accelerate the craft, the technological development spanning perhaps centuries, the opportunity cost of what else that effort could accomplish, are staggering. Could those resources better serve humanity by solving problems at home? Poverty, disease, environmental degradation, social injustice. Does a species that hasn't achieved sustainability on its home planet deserve to spread beyond it? And who decides to commit future generations to such a project? The people who launch the mission won't see its outcome. They're spending resources and making decisions that bind their descendants for millions of years. There's also the question of whether the journey itself becomes the point, rendering the destination almost irrelevant. The spacecraft would generate knowledge throughout its voyage, mapping dark matter, observing galaxies from unique vantage points, testing technologies across timescales impossible to replicate otherwise, potentially discovering unexpected phenomena in intergalactic space. The engineering required to build such a craft would advance human technology dramatically. The social systems needed to maintain purpose across generations would teach us about long-term thinking and institutional stability. Perhaps the mission's value lies not in reaching Andromeda, but in becoming the kind of species capable of attempting it, in developing the wisdom, unity, and technical sophistication such a project demands. Ultimately, perhaps the Andromeda mission exists at the boundary between practical achievement and philosophical statement. We might never actually attempt it, but contemplating it forces us to confront what we value, what we're willing to sacrifice for knowledge, and how far our ambitions extend. It asks whether humanity's destiny is to remain a single-planet species in one galaxy, or whether we aspire to something larger, even if reaching it takes millions of years and transforms us beyond recognition in the process. Having contemplated why we might go to Andromeda, we must now confront a stark reality that fundamentally changes the nature of this mission. There is no coming home. Unlike every other journey humans have undertaken, expeditions to Antarctica, voyages to the Moon, even proposed missions to Mars, an Andromeda mission would be irrevocably one way. The return journey isn't merely difficult or expensive, it's essentially impossible, and understanding why reveals the profound finality of crossing intergalactic space. The most obvious problem is propulsion. Reaching Andromeda requires nearly all conceivable energy and fuel, whether antimatter, fusion fuel, or the kinetic energy imparted by laser arrays back home. Once there, the spacecraft would have none of the infrastructure that enabled its departure. There's no massive laser installation in Andromeda to push a solar sail back toward the Milky Way, no fuel refineries to manufacture antimatter, no civilization to support the return mission. The ship would need to carry enough fuel for both the outbound journey and the return from the moment it launched. But as we've discussed, the tyranny of the rocket equation makes this impossible. Accelerating fuel to relativistic speeds requires more fuel, which requires more fuel to accelerate, in a vicious cycle. Carrying return fuel effectively doubles or triples the initial mass, requiring exponentially more energy to launch. Any realistic mission design exhausts its propulsion capability reaching the destination. Even if we imagined perfect fuel efficiency and carried enough for a return, the journey would take another 2.5 million years minimum, creating a round trip of 5 million years. During this time, Earth wouldn't simply age, it would transform beyond recognition. 5 million years ago, our planet looked utterly different. Antarctica had ice sheets, but Greenland didn't. The Isthmus of Panama hadn't fully formed, and our hominin ancestors were barely distinguishable from other apes. In 5 million years, continental drift will have moved land masses measurably. Africa will have moved closer to Europe, closing the Mediterranean. The East African rift will have widened. Coastlines will have shifted dramatically. Mountain ranges will have eroded, new ones thrust up, and the geography of Earth will be alien to anyone who left. The biological changes would be even more dramatic. 5 million years provides ample time for significant evolution. Every species currently alive would either be extinct or evolved into descendant forms potentially unrecognizable as related to their ancestors. Humans themselves, if we survive, would likely evolve into something different. Pressures from climate, technology, or deliberate genetic modification could produce post-human species as different from us as we are from our Australopithecine forebears. The returning crew would find not their descendants, but alien intelligences that might share some genetic heritage, but would be culturally, linguistically, and possibly biologically incompatible with the voyagers who left 5 million years earlier. Human civilization and culture would certainly not survive intact across such timescales. 5 million years dwarfs all of human history by 3 orders of magnitude. The oldest human civilizations, Mesopotamia, Egypt, the Indus Valley, emerged merely 5,000 years ago, 1,000th of the return journey time. In 5 million years, languages would evolve beyond any mutual intelligibility. Romance languages diverged from Latin in just 2,000 years. Multiply that process by 2,500 and no linguistic connection would remain. The very concept of humanity as we understand it, our values, our identity, what we consider important, would have transformed completely. The returning crew would be time travelers from an incomprehensibly distant past, their culture and knowledge as ancient and alien as the Paleolithic is to us, but far more so. Technologically, Earth might be unrecognizable or might not exist at all. Perhaps humanity will have spread throughout the galaxy, rendering Earth an abandoned backwater or a carefully preserved museum. Perhaps we'll have transcended biological existence entirely, existing as digital consciousness or having merged with artificial intelligence in ways we can't currently imagine. Perhaps we'll have destroyed ourselves, leaving Earth a lifeless ruin or recovering biosphere with no trace of human civilization. Perhaps some other species will have inherited Earth, evolved from surviving animals after humans vanished. The crew cannot know what they'll find because 5 million years is enough time for essentially any scenario to play out. This temporal gulf creates profound psychological implications for any conscious crew. Launching means accepting total severance not just from home, but from time itself. Everyone you know will be dead. Not just elderly, but dust. Their bones fossilized or eroded away. Their very species possibly extinct. The entire historical epoch you lived in will be forgotten. Your civilization collapsed and buried under geological layers of time. You become an exile not just in space, but in time, unable ever to return to the world you knew, because that world will have ceased to exist, not through destruction, but through the inexorable transformation of deep time. This finality might actually argue for an AI mission rather than biological crew. An artificial intelligence doesn't have a home to return to in the same way, doesn't experience the psychological trauma of permanent exile, and doesn't mourn the loss of the familiar. An AI could complete the mission, gather data, and perhaps transmit findings back. Knowing the transmission takes millions of years, but not caring in the way a human would. The one-way nature of the journey reveals that perhaps this is fundamentally a mission for machines, not for living beings. A voyage beyond the boundaries of what biology and human psychology can endure. As we contemplate our impossible journey across 2.5 million light-years, zooming out to the ultimate cosmic perspective reveals a profound irony. We don't actually need to go to Andromeda, because Andromeda is coming to us. In approximately 4 to 5 billion years, our 2 galaxies will collide and merge into a single elliptical galaxy astronomers have already nicknamed Andromeda. The collision has already begun in slow motion. Andromeda approaches at 68 miles per second, drawn by mutual gravity across the shrinking gap. When the galaxies interpenetrate, individual stellar collisions will be rare due to vast distances between stars, but gravitational interactions will fling stars into new orbits, triggering waves of star formation as gas clouds collide, and eventually the 2 supermassive black holes at each galactic center will spiral together and merge. Our hypothetical million-year voyage, our tremendous expenditure of energy and resources, our crews exiled across time, all of it rendered quaint and unnecessary by the patient inevitability of gravity. The universe itself will accomplish what we strive for, given enough time. This cosmic timeline humbles our ambitions while simultaneously elevating them. We seek to touch Andromeda not because we must, but because waiting billions of years offends our urgency, our desire to explore now rather than letting the cosmos unfold at its own pace. Our journey, if ever attempted, becomes not practical necessity but defiant impatience, humanity refusing to wait for the universe to bring the destination to us, insisting on reaching out across the void on our own terms, in our own time, however impossible that may be. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.